This was the magnetic field on the axis of a circular current carrying loop. Here the current carrying by the loop is I and radius of the loop is R, single turn, one turn of the loop only, and distance of the point P from the center is equal to x. P is on the axis of the dipole. This ring or this coil, axis of the circular current carrying coil, and this was the formula of the magnetic field, mu naught I r square by 2 r square plus x square to the power 3 by 2. From this idea we will derive the field on the axis of a solenoid, inside the solenoid. So this will be question number 7. So to find the field, I mean the magnetic field on the axis of the solenoid, and for the solenoid this is the current, I is the current, and n, this small n, is number of turns per unit length on a solenoid. You know, there are huge number of turns, and the point P will be specified by this. It will subtend some angle at the ends of the solenoid, which will be shown by this. See, this angle is, this is phi 1 and this angle is phi 2, and this is the solenoid and the current carried by the solenoid, like this. These are the turns of the solenoid. Okay. So here what we will do is that we will consider a coil here. We consider a coil like this. Now let the distance of the point P from the center of the coil be x, and hence as this distance is x, so the thickness of the coil will be dx. So the thickness of the coil will, and here it subtends an angle like this, phi. Subtends an angle phi like this. Okay. So what are the number of turns on the coil? Number of turns on the coil is equal to n times dx. N is number of turns for unit length, so for length dx, dx is the thickness of the coil, so for length dx the number of turns is n multiplied by this thickness dx. Let's draw one more diagram for this. This is the coil, this is the point P, this distance is x, and this distance happens to be dx. Okay. So this is the coil this way. So the current depends, it follows the right hand thumb rule. Actually this also follows the right hand thumb rule. So if your thumb is like this, and okay, so this is, if this is the current, if this is the direction of current, this is the direction of magnetic field, and vice versa also. It happens vice versa also. If this is the direction of current, this would be the direction of magnetic field lines. Okay, by the way, so due to this coil, now this angle is phi. Okay, and what is this radius? Say it's r, radius is r, so this is phi, this is also phi. Okay. So x is equal to r times tan phi, right? Okay, so due to the coil of number of turns, this n times dx, the magnetic field at P is equal to what was the formula? We'll use that, mu 0 into I into r square. Now I'll have to multiply the number of turns, n dx divided by 2 into r square plus x square to the power 3 by 2. Okay. This is due to the coil. So what is the total field? Total field, then you have to add up all the coils, right from, so if you include all the coils, then you there's a full solenoid actually. So phi will vary from where? Let's see this diagram again. As given in the problem, this is the point P and that's phi 1 and this angle is phi 2. So phi will vary from minus phi 2 to phi 1. So phi will vary from minus phi 2 to plus phi 1. Okay, so let's find the field. So it's integral of mu naught I r square n times dx divided by 2 r square plus x square to the power 3 by 2. Now we know that x is equal to, from the diagram, x is equal to r times tan phi. So therefore dx equal to r sec square phi d phi. So I'll put it here, r square n times dx. So r sec square phi d phi, and downstairs you have that will be r cube. This is 1 plus tan square theta sec square theta, so sec cube theta. So that will go on top to become cos theta. So mu naught I r square, oh that's r cube, that's gone, n, okay, by 2. So integral of cos phi d phi from minus phi 2 to plus phi 1. So integral cos phi d phi from minus phi 2 to plus phi 1. So mu 0 ni by 2. So that's sin phi from minus phi 2 to plus phi 1. So if you put the limits, then you get b is equal to mu 0 ni by 2 sin phi 1 plus sin phi 2, or you can write mu 0 ni by 2 cos alpha 1 plus cos alpha 2. Now just I'll show the diagram. This is the solenoid and this is the point P where you have to find the field. This current flows in the solenoid and these are the angles. If you express in terms of phi 1, phi 2, or if you express in terms of this angle alpha 1 and alpha 2. So please remember this formula. Now we will deal with a special case. We will find out the magnetic field inside an infinite solenoid. That means a solenoid of infinite length. So this will be question number 8 actually, special case of 7. So magnetic field inside, that is on the axis of infinite solenoid, or say infinite length solenoid having n is turns per unit length and I is the current. See, special case, infinitely long. See, infinitely long means actually the length is much larger compared to the radius, and this point P is between. So as you see, this phi 1 and phi 2 for infinite length, both will be how much? Phi 1 and phi 2 both will be equal to pi by 2. So the field equal to mu 0 ni by 2, 1 plus 1, mu 0 ni by 2 sin phi 1, 1 for sin phi 1, 1 for sin phi 2. So that's B equal to mu 0 ni. This is at the middle. Now at the ends, what will be the field? At the ends of infinite solenoid, say this is the end, this is at one end of the solenoid. So here phi 1, actually here see phi 1 is pi by 2 and phi 2 would be this angle, right? This angle. So that's 0 actually. Phi 2 is 0. So B here at this point, B equal to mu 0 ni by 2 sin phi 1 1 and sin phi 2 0. So mu 0 ni divided by 2. So what happens actually here? So for the infinite length solenoid, if I draw this a long solenoid, long means the radius is very small compared to the length. So if I draw the magnetic field versus x, B versus x, so round about the middle part, the field is, as you have seen the formula, mu 0 ni. So it's approximately mu 0 ni for a long solenoid, remember. And at the end it decreases to half of it. So it's like this. The graph will be like this. This is mu 0 ni, and at the ends it is half of mu 0 ni. This is for a, this happens for a long solenoid, okay. And for a short solenoid, for a long solenoid, what happens in the majority of this region inside, you will get approximately a constant value throughout a large region inside. Approximately you have a constant value mu 0 ni, constant value rather, mu 0 ni. But for a short solenoid, it won't be like this. For a short solenoid, you know, this will be the curve. Short solenoid means the radius is comparable to its length. Okay. So that's for a long solenoid. Now this I am drawing for a short solenoid. Somewhat at the middle it is highest and somewhat gradual decay, right? So next we'll be learning about Ampere's law.